So as we are graphing inverse functions, we want to think about what we just learned for the definition. We know that a function f and its inverse f inverse are related to each other, where if a point a, b is on the graph of f, then we have a corresponding point b, a that must lie on the graph of the inverse and vice versa. This means that the graph of the inverse function f is a reflection of that original function f. You can see a diagram here. This picture shows that these points are reflections of each other, and they're reflections over this line y equals x. So every inverse is a reflection over that identity line. In example 4, we have a graph that is 1 to 1. So this function f would pass the horizontal line test, so it is 1 to 1. And we can describe its domain and range. The domain of f is from -1 to +2. Every x value from -1 to +2 has an output. And the range of f is from -3 to +3. Every y value from -3 to +3 shows up somewhere in the graph. So to do the inverse, we want to graph as many inverse points as we can. This graph has a point at -1, -3. The inverse of that point would be -3, -1. We have a endpoint of 2, 3. Its inverse would be 3, 2. But we want to graph more than just 2 points, and this might mean that we have to estimate some, and that's okay. So if I look at the y-intercept, this y-intercept is -2 point something. It's a little bit before halfway between -2 and 3, so maybe -2.4. That means that the inverse point would be -2.40. We can continue to find more points. This looks like there's a point here at 1/2, -1.5 here. So if I do the inverse, we would be at -1.5, 1/2. We could find the inverse of this x-intercept. That's at maybe 1.10, so the inverse would be 0, 1.1. And the more you do this, the more points you have to graph. We can see that inverse graph takes shape. So there is our inverse function f inverse of x. If I look at the domain of that function, the domain of this starts from -3 to +3. The range of that function is from -1 to +2. Now hopefully you see some similarities of what just happened there, but the domain of the original function should be the same as the range to the inverse function. And remember, that's because when we're looking at that mapping diagram, there is a function f that will map a domain to some output range. That means there's a unique inverse function, f inverse, that maps that range to the original domain. So there is this inverse relationship going on here, So the last thing in part D wanted us to do was to draw the reflection line y equals x. This reflection line is a diagonal line with a slope of 1. Looks something like this, and we can see that's where that line of symmetry is for this reflection. So go ahead and pause and try the second graph on your own. You've got this 1-to-1 function here, and you want to graph the inverse of this. So if you're ready, you've already done this. We're going to do it together real quick. The domain of f was from -2 to 4, so I would say domain of f with a subscript here, -2 to 4. The range of f is from -4 to +4. That, excuse me, from right there, we can figure out what the domain and range of the inverse are without even graphing. So the domain of the inverse should be the same as the range of f, and the range of the inverse should be the same as the domain of f. Lastly, we want to actually make a graph. So if I look at each coordinate and do the inverse, -2, -4 has an inverse of -4, -2. There was a point at -1, -1, and its inverse is the same point. There's a point at 0, 2, so its inverse would be 2, 0. Point at 2, 3 becomes the inverse 3, 2. And lastly, we had 4, 4. So the inverse function graph looks like this. I always try to do this in another color just to make sure it's clear where the inverse actually is. And if I draw that identity line, it will look something like this. You can see that anytime that a point was the same, it is on that identity line because the inverse of that is the exact same. All right, and so in the next video, we're going to look at these algebraically.